Okay, without any further delays, I'll introduce you to the man of the hour, Ed Sudicky. Ed is a professor emeritus in the Department of Earth and Environmental Sciences at the University of Waterloo. He's been on the faculty since 1985. He's one of the founders here at Aquanty and continues to work with the team as our scientific lead and as the chairman of the board. Ed is the recipient of several international awards and honors for his research contributions to the field of integrated hydrologic modeling. Those awards include the NGWA Henry Darcy Distinguished Lecturer Award in 1944, the M. King Hubbard Award in 2007, the Geological Society of America Meinzer Award in 1999, the American Geophysical Union Hydrology Award 2002. He's also a fellow of the Royal Society of Canada, the Canadian Academy of Engineering, the American Geophysical Union, and the Geological Society of America. So, quite the resume, Ed. He's a true leader in the field of integrated hydrologic modeling, and today he's going to be discussing advances in this field and future areas for research and development with integrated hydrologic models, a little bit about what Aquanty has been working on in the past couple of years. So that's it for me. Ed, take it away, and with one more quick reminder to everyone to please turn off your videos. Thank you.
All right, welcome everyone. It's nice to see so many people attending this webinar. Oh, and Braden, just one reminder, my Darcy lecture was in 1994, not 1944. I'm not quite that old. So yes, welcome. We have people from various sectors, academia, industry, government, consulting, a number of different countries. So I'm very pleased that you could all attend. My purpose today is just to introduce you to fully integrated modeling, what we do at Aquanty, who we are, a little bit on that. I'll briefly touch on some of the features of HydroGeoSphere, and then I'll present a number of examples on how we use it to actually solve problems at various scales. This is not a tutorial on how to bring data into HydroGeoSphere and how to execute it and so on. So keep that in mind. Braden, I know, does give periodically tutorials on how to use HydroGeoSphere. Next slide, Braden. So a little bit about Aquanty. So it was founded in January of 2012, so almost 10 years ago, by the core developers of HGS, including myself, Renee Terrian, Peter Forsyth, shown here on the screen. It's the result of, well, almost 25 years of research and development at Waterloo, as well as Laval University. Aquanty has grown over the last 10 years, and we continue to grow. Currently, we have 12 PhDs on staff, 4 MSc, MASc, and 3 bachelor's level people. If you check out our website, you'll notice that we are advertising for at least 3, maybe 4 more people. So have a look at it. The staff have specialties in many areas, not just hydrogeology, but also soil physics, climate system modeling. We have applied mathematicians, and of course, integrated subsurface surface modelers. And we're showing, I don't know, 15 or so people here. The list may be a little bit out of date, and the board of directors are listed down at the bottom. Next slide, please. So where did all this integrated modeling begin? Well, Al Fries, along with Russ Harlan, wrote a paper published in Journal Hydrology in 1969, which was a blueprint for a physically based, digitally simulated hydrologic response model. I've known Al since I was doing my master's, so about 45 years. Al was really, and still is, a very gifted person with a tremendous amount of vision. Over his career, he introduced many new topics to the field of hydrology and hydrogeology. This was one of the early ones, which really set the stage for everything that we're going to talk about today as well as other researchers around the world that have developed integrated models. Next slide. So in their paper, they pose some questions, which are paraphrased here. You know, can we really do this? And this, you got to think back, this was 1969. One of the questions was, do we understand the key water cycle processes well enough to represent them with a numerical model? And here I've just listed some of the equations we use in HydroGeoSphere. They're nonlinear equations, which I'll show more equations a little later on. Second question was, does the data exist to build such models? They're pretty data hungry. You need subsurface information, the hydrostratigraphy, soil materials, land cover, weather, etc., to drive the model. That's a pretty extensive list. And groups have been grappling with this question for many decades, typically separately, surface water hydrologists and subsurface hydrologists commonly going their own way. And then finally, do we have the computational resources to run the simulations in a reasonably time framework? As I said, these are very nonlinear systems. They're very challenging to solve. If you want to solve a large problem, your meshes are going to be very large, many degrees of freedom. And some people are still asking whether or not this can actually be done. Next slide, please. So here's a picture of Al Freeze, taken quite recently on the right, and Craig Simmons, who actually brought him to Australia to interview him about his initial paper and his thoughts and what went into it and where we thought it might go. And Craig and several of us just published a paper in the journal Hydrology, same journal that Al published his a couple of years ago, a year and a half ago, commemorating the writing of Freeze and Harlan paper. It was the 50th anniversary. And I encourage you to read the paper. Al's thoughts and things that were going through his mind at the time are presented through the interviews in the paper. And then there's a little bit of history in the paper and sort of where it's led up to today. And on the right is just a conceptual diagram that Al had put in the paper, showing a 3D flow system with inputs such as precipitation, outputs such as ET, runoff. And he had in mind at the time a finite difference type model. Next slide, please. So we looked at something that was kind of interesting. This would be a couple of years ago, on the citations to the Freeze and Harlan paper over the years. So it's sort of picking up a few citations, mid-70s, early 70s. Al had published a couple of papers with grad students looking at hill slope hydrology with this integrated approach, but it didn't really pick up steam until later years. I show here sort of 1994 Frac 3DVS. That was developed by René Terrien as a PhD student under me. He is now a full professor at Laval University, and that's the subsurface part of HydroGeoSphere as it was originally developed. And a subsequent student came along, PhD student, and he added some surface water aspects to basically Frac 3DVS. That was NHM. That was sort of 1999. And then an opportunity arose where Renee and I got together again and kind of took Frac 3DVS, some concepts and ideas from our co-worker, Dr. Peter Forsyth, who is special skills in solving nonlinear partial differential equations and sparse matrix solvers, and we put together HGS. So that'd be about 2001, thereabouts. And people started writing papers and citing Al's paper. about sort of picked up about that time frame. Power flow came along a few years later. That's Reed Maxwell and Stefan Collette, sort of US-Germany collaboration, started picking up a little more. More papers were being written, more citations to L in the Harlan paper. And then Aquanty, I'm showing where it was formed in 2012. And that curve just keeps rising, it seems. So it's integrated modeling is definitely a concept that's picking up in the literature. Next slide, please. Here's a few existing models. This is by no means a comprehensive list. I mentioned NHM, kind of a precursor to HydroGeoSphere, Mod HMS from HydroGeologic Inc. out of the States, PowerFlow, OpenGeoSys out of Germany, Cathy out of Italy, the Penn State Integrated Hydrologic Model, and so on. There are a number of others. So it seems to be a growing area of model development, but one of the questions I had, do we need more models or perhaps more applications that are with such models that are centered on resolving key societal concerns and scientific questions? Next slide. So kind of this slide, I'm attempting to depict the evolution of hydrologic simulation. So if we look at upper left, you know, we have maybe lumped hydrologic response unit based models. They're not based on nonlinear partial differential equations, routing rules, and so on and so forth. Examples might be the USGS precipitation runoff modeling system, PRIMS, Watt Flood, which originated out of University of Waterloo, a former professor of mine. I think it's now called, or a version of it's called MESH within Environment Canada. The Cold Regions Hydrologic Model out of the University of Saskatchewan. But they typically don't include groundwater. Then there's a class of models, which I'll call distributed PDE, but they're surface-only models, and they're typically used for flood event forecasting. SHE, 2-flow, J-flow, and so on. There are others. Now in the groundwater domain, of course, everyone is familiar with ModFlow, originally a fully saturated model, so below the water table only, although it's many packages have been written for it. Sort of wet-dry cell packages, which you're not really solving Richard's equation, but you're allowing the water table to move. Beyond that, then there's 3D variably saturated models, which are valid above and below the water table. Frac-GDS, which I already mentioned. FEFlow, which is quite a popular model. Hydrus, also very popular. Origins with an old friend of mine, Rien van Gunupten. I'm sure many of you heard of the van Gunupten equations. Now, as we move to the right, we're attempting to bring in more physical realism, numerical sophistication, and this is the coupled surface water groundwater models. And there's kind of two families of models in a general sense. There are linked models where you have different compartments. For example, the land surface compartment, which is linked to the unsaturated zone compartment, commonly represented as a 1D vertical infiltration, exfiltration process, and then linked to a third of the saturated zone. More recently, in the last, as I said, 10, 15 or so years, all of these equations can be solved in a globally implicit way. You solve all the nonlinear surface and subsurface equations simultaneously at each time step. We'll refer to that as tightly coupled. Examples are HydroGeoSphere, PowerFlow, OpenGeoSys, Penn State Integrated Hydrologic Model, and so on. So that's just kind of a very rudimentary overview of where we're going. Next slide. Here's a typical compartmentalized land surface approach, CLM or other kinds of models, where you have all these different compartments. They're linked together and they communicate with each other, but groundwater is typically not represented in a physical way. They sometimes talk about inactive groundwater storage versus active groundwater storage, which somehow leads to base flow. So we wanted in HydroGeoSphere and others who have developed integrated models sort of move away from the compartment approach, more towards partial differential equations, and include groundwater in a mechanistic way. Next slide. So here's kind of a picture that illustrates the water cycle and all its various components and pieces. And HydroGeoSphere, as I mentioned, tries to solve all this in one single globally implicit fashion in 3D. So we include overland flow, surface runoff, stream flow, infiltration, exfiltration, groundwater flow, groundwater feeding the streams, evapotranspiration, snow melt, all of these things. And the model is driven by either weather forecasts or perhaps climate projections. Those are the only things driving the model. It's a complicated system, highly nonlinear. So we make use of very advanced numerical methods, very advanced sparse matrix solver, parallel computing, and more recently, cloud computing. Some of the, I won't mention all the features, but some of the things we do, which is a little bit beyond the norm, I would say, adaptive time stepping. So the time steps are controlled internally by the model. So if you, for example, turn on a well or you have an intense rainfall event causing flooding, it will automatically cut time steps until the system starts to settle down. Then it will automatically increase time steps, and that can be user controlled. Flexible meshing, we use unstructured meshes for the most part. So with unstructured meshes, you can concentrate your nodal spacings or the size of your elements in finer spacing in areas where you expect higher gradients and so on. Or flatten out the, or widen the nodal spacing where you expect less response. You can it's quite flexible. You can reduce process complexity as well as dimensionality. For example, you can turn off the entire subsurface and just do surface modeling, or you can turn off the surface and just do subsurface modeling, or you can turn everything off and just do mod flow style groundwater modeling. It can accommodate solute transport, heat transport, discrete fracture networks, density-dependent flow, saltwater intrusion as an example, dual porosity, dual permeability formulation, winter processes, et cetera, et cetera. Next slide, please. Since Aquanty has been around, there's been quite a widespread increase in users, strong scientific publication record with HGS, not just by the Aquanty team, by users around the world, many citations. We like to have close ties with academic institutions. For example, 4 or 5 of the Aquanty staff are adjunct professors at the University of Waterloo, and the users are comprised of academic, commercial, government, etc. Next slide. Oh, I think we went one too far. Can you go back one, Braden? There, no, one. Oh, okay. And here's an overview. I'm not going to go through all of these in detail because I've pretty much outlined that already. In terms of the 2D overland flow, it's kind of interesting. You can start the model out with no surface water at all, no lakes, no rivers flowing, water table and arbitrary depth, and you can begin raining on it or applying precipitation during a spin-up process. And if you get things right, the geometry, the hydrology, the hydraulic properties, the DEM, it will actually form the drainage network. In other words, the rivers and streams, the wetlands, the lakes, etc., which is kind of really interesting to watch this evolve. Of course, we include, things like evapotranspiration. That's embedded as a nonlinear term within the 3D Richards equation for variably saturated flow. As I said, you can include macropores and fractures and so on and so forth. It does do advective, dispersive, reactive transport. It can include winter processes. And it's been parallelized using the OpenMP shared memory framework. We find that works best for us. Next slide. Here's a couple more articles you might want to take a look at. These are a couple of papers published a few years ago by a whole bunch of us that are involved in developing integrated models. And they're two papers that present some benchmark problems. People often ask, well, how do I know which model, how it performs in this situation versus that situation, or how does it handle this process versus that process? And these example problems, although fairly simple, try to answer some of or address some of these questions. So please have a look at them. They were published in Water Resource Research. Next slide. So, equations. I'm not going to dwell on them. Most of you are familiar with equations, so you probably would be bored anyway. So on the left, a couple of equations we have in the upper, delta and omega q, gamma naught, plus or minus q, etc. That's the 3D form of Richards equation. There's actually another term that's added on the right-hand side, which includes specific storage. And in the bottom is the two-dimensional form of the diffusion wave equation. So it's like the St. Bernard equations, so we threw out the momentum term in this case. Now this term gamma naught, that's what connects the two equations. You see the arrows two-way. That's the exchange of water between the surface and the subsurface domain. And we use the first order exchange process described below in order to make that connection. So there is a relative permeability term in that gamma naught, a hydraulic conductance term, and then sort of the difference, if you will, in the pressure or the head between the surface and the subsurface domain. So there's interaction, there's feedback. By solving everything simultaneously at each time step, we find that it eliminates convergence difficulties. By the way, we use nude iteration in a very efficient method for assembling the Jacobian matrix. And these exchange relationships are given explicit definitions. Next slide. And here I'm showing the advection dispersion equations. Again, the upper equation is the 3D form of the subsurface flow transport equation. There's some reaction terms and so on. I think we have a capability to do geochemical reactions, although we don't often use it. And the equation below is the 2D over the land surface transport equation for solutes, including the transport of solutes that enter into a stream, either from the groundwater system or maybe overland flow from a farm field. And like the water exchange, we have a solute exchange flux. The first term on the right-hand side of that equation is simply the advective transfer of solutes between the two domains. C ups is an upstream concentration. Gamma naught, if you recall, is the water exchange. And then a first-order representation of the diffusive transfer of solutes between the surface and subsurface domains. Again, these equations are solved simultaneously in both the surface and the subsurface at each time step. Next slide. Couple little details which are kind of interesting and very useful. Conceptualization of microtopography and flow through the vegetation on the land surface. I won't go through all of the details, but you can see the brown, that sort of undulating topography, let's say within an element, that forms an impedant to horizontal flow until the water level rises above the height of that microtopography. Now, once you go above the height of the microtopography, there's still an impedance of flow to flow because of the presence of vegetation. And then finally, if you go above the vegetation, it's sort of a free flow. So we can control the horizontal flow above these various heights and also use a relative permeability term to control the resistance to flow. And then on the diagram, oops, back one, on the right, we can accommodate the water stored within the microtopography and within the vegetation. So that becomes very useful if you have small features, as we have used in the Western Canada, called prairie potholes or small ponds, that you can't explicitly discretize within your numerical model. We can use this representation to basically bring them into the picture of their storage and resistance to flow capabilities. Next slide. Evapotranspiration and interception, sort of a top-down approach. The leaf area index plays a major role in interception storage. Once that is filled, then you can have recharge to the groundwater, rainfall falling to the ground. The total, you have to specify potential evapotranspiration in the HGS, air temperature and things like that. That's first met from interception storage, and the remaining PET is taken up by either transpiration by the plants or evaporation from bare soil. And of course, transpiration is we treat as a function of leaf area index, moisture content, and root distribution function. Now, these things can vary with time. Leaf area index, that changes with season, with crops, and so on. We actually can use satellite imaging to kind of accommodate for or parameterize things like LAE or rooting depth we can estimate from literature studies. Next slide. Excuse me. So in HGS, we use typically a 3D finite element mesh, control volume finite element mesh. It's mass conservative even locally. Just showing a mesh here. It happens to be for the Grand River watershed, which Waterloo sits on, Waterloo region. And we use different types of elements. The sort of brick type element, 8-noded, is one example. But what we commonly use is prisms, the triangular prism element shown there. And a mesh generator, we use Algo Mesh, comes out of Australia. We have a good connection with them. It's one of the finest mesh generators I have ever seen. There is also an option to break down these types of elements into other tetrahedra, although we don't normally use them. You get into very high element counts for some of these very large problems. Next slide. At Aquanty, most of our applications within the office to date have been directly involving us, have been Canadian applications. And this just shows some of the basins and watersheds that we have worked on or currently worked on. There's the Southern Ontario, the Great Lakes, which I'll talk about a little more. Athabasca in Western Canada, which I'll briefly talk about, that contains the oil sands region, and the Assiniboine, South Saskatchewan River Basin. But we've also have been in the past worked on a model of all of Canada in 3D. And at the end of my talk, I'll briefly introduce a new project where we're breaking all of Canada up into half a dozen subbasins in fair detail to do a Canada scale model. Next slide. So we've been looking at developing models at a broad range of scales, typically major river basins with areas of about 150,000 square kilometers. A reasonable degree of resolution of the model. As I mentioned, with unstructured meshes, you can put finer node spacing where you need it and broaden it out where it's perhaps not so necessary. But in some cases, you want to look in much more detail, perhaps at a sub-basin or even a regional scale of 500 square kilometers. We can telescope in with the outer models driving the inner model via boundary conditions. So outer model can supply information to the inner model. So there is consistency across scales on water balances and so on. This is I guess I could say semi-automated. Maybe one day we'll get fully automated on this. But as you go finer in scale, of course, you can also increase the resolution of, for example, the hydrostratigraphy, the land cover, the soil materials, and so on and so forth. So this is kind of how we do the telescoping. Next slide. Now, how do we construct these models? Well, as I said at the beginning, they're quite data hungry. We can start with a climatology. Maybe it's weather forecasts, or perhaps it's a climate projection, which drives the model. Then you need information on the land cover, the type of vegetation, things like leaf area index. Some of these things you can gather from satellite information on a time-dependent basis. Of course, you need the soils, shallow soils, maybe the first meter or so. Much of this is available. And then there's the subsurface geology or hydrostratigraphy, which controls the deeper groundwater flow. What we found, at least in Canada, and I think it's probably true in other countries such as US, some European countries, these data sets are publicly available for the most part. And certainly in a degree sufficient enough to build a plausible integrated hydrologic model. Next slide. Example inputs. If you could just click through these, Braden. So output of the model, one of them is recharge or discharge. So recharge is actually something that's calculated internally as well as discharge to the land surface. It's not an input. Modflow, for example, you specify recharge. Well, here it's calculated. Of course, you get surface water flow, the hydrographs in the streams, soil saturations, surface water levels, either in the streams or lakes, and of course the subsurface, hydraulic heads, water table position, and so on. So these are all outputs that can be put out from the model at every time step, or chosen time steps, or chosen locations. Other things that are output include evapotranspiration rates. If you're doing solute transport, you get concentrations. Standing water, for example, in fields. The way HydroGeoSphere is constructed, if you have a lowland area, perhaps in a farmer's field, it's not directly connected to a stream. Water can still pond up at that location. Next slide. This is just a little animation. There was a flood 2013. This is Western Canada, a city. And you can see on the left, sort of colorized, the flooding of the stream, that circular region of wastewater treatment plant that was actually flooded. And then a full 3D perspective is shown in the right-hand panel. And it actually agreed extremely well what was mapped during the flooding event. Now, what we did, we took a larger model, one of the Western Canada models. We took the stream flow from the larger scale model and then input that stream flow to the left-hand side of the input stream and created a much, much higher resolution model. So this is an example of the telescoping to gain resolution. Next slide. I mentioned fractures and control structures and so on. This is just a simple 2D cross-section. Upper diagram is an unprotected river channel in a valley, floodplain, whereas in the lower diagram, we've inserted some levees, if you will, to try and contain the flooding so it doesn't spill over into the floodplain. What's interesting, you can see below that, a little bit of groundwater peeking up into the floodplain, just on the sort of outboard side of the dikes. So that's kind of interesting. You can actually use it to design flood control structures. Next slide. And here's where we did a little problem. This was High River, Alberta, again, that June 13 flood, where we inserted in the model, if you look at that rotating thing, you can see some flood prevention dikes that were put into the model. Then you'll see a flood wave coming through, and it protects the urban area in sort of the lower part of the domain, where the urbanized area is. And that was quite effective. We can build these models quite rapidly, actually. And you can do scenario analysis and so on and so forth. All right, next slide. Fractures. Again, just a simple cross-sectional example. This is a really hard problem to solve, really crazy nonlinearities. You can see there's precipitation applied in the sort of top left portion above pothole 1. It spills overland into pothole 2. Then you get an infiltration front that reaches down to that clay aquitard that has a few fractures in it. It penetrates those fractures, and then you see the water table responding to this recharge in that lower aquifer. As I mentioned, this is a really hard nonlinear problem to solve, and HydroGeoSphere seems to be able to handle it quite well. Next slide. Okay, a couple of larger examples. Athabasca River Basin, we've been working on it for quite a long time. We've done a lot of work in the oil sands region, and this is a regional model of the entire basin. There was lots of good information to build the subsurface geology, populate the surface in the usual way. Excuse me. And we have used this model to look at climate projections, more recently an ensemble of climate projections, and how that affects maybe oil sand operations, the availability or non-availability of water for their operations, and so on and so forth. I think we published 1 or 2 papers in Journal Hydrology on this modeling. Next slide. And it performed quite well. We do the calibration with historic climate. I'm just showing the simulated flow rate at a number of gauging stations, simulated heads in the subsurface versus observed, and then stream flow, just showing here the Fort McMurray. So it did quite well. It's not perfect, but no model's perfect. We all know that. Next slide. And this is kind of interesting. On the left panel versus the right panel, we have on the left with peatland processes, wetlands, and winter processes. And this is at Fort McMurray. This is stream flow versus time. We actually get quite a good representation of flow through the time. If we don't include winter processes and wetlands, a very different response. It's very different from what the observations are. So it just highlights the importance of including these types of processes. And with HydroGeoSphere, you have that flexibility to include or not include processes to assess what their relative importance is. And that gives you useful insights. Next slide. We also published a paper recently on a model, I think it was Journal Hydrology again. We developed a 3D surface-subsurface model of the entire Great Lakes Basin. That worked out pretty well. There's a lot of interest in the Great Lakes Basin because of the International Joint Commission. It's an agreement between Canada and the US to maintain and protect water within the Great Lakes. Next slide. So there's the paper. 2020 it was published. You can see the domain, the resulting finite element mesh. If you read the paper, we kind of concluded we probably need to go finer on the mesh, which we could, but that's for future consideration. I think the total area of the basin, including the lakes, is about 550,000 square kilometers. Next slide. So lots of data, again, that's needed. We just searched through the literature, soil we got from USDA Soil Landscapes of Canada. You can see the patchwork of different soil types. You can assign hydraulic properties to them depending on their textural properties using Rosetta to come up with relative permeabilities and soil moisture characteristic curves. And then using various sources, we put together the geology. I think it was 8 layers in the subsurface, quaternary layers down into the bedrock. Next slide. This is a dynamic spin-up. So we started everything dry. We're spinning up the model with sort of average precipitation. You can actually see the Great Lakes filling up, the streams beginning to form, Niagara Lake or Niagara River there is flowing. So it's kind of interesting that, you know, this, once you got it spun up to kind of a quasi-steady state, then we can apply, you know, actual precipitation to the model and drive it through time. Next slide. And it actually did a pretty good job. We used monthly normal forcing from NRCan, Natural Resources Canada. And this is at a number of gauging stations, stream flows. Smaller streams, larger streams, including Niagara River, St. Lawrence, which had to do a little bit of scaling because our domain there did not include sort of all of the drainage area that feeds into the St. Lawrence, but overall quite good. Next slide. And not too bad for water levels in the subsurface, the bedrock, as well as the overburden. Again, it's tricky to compare these because some water levels were collected at many different times and different seasons, different years, but overall, it's okay. Next slide. And one of the things, or question being asked within IJC is how much groundwater actually get into the lakes as either direct or indirect discharge. And we actually can calculate that within HGS. And this is the average annual. So, and of course, during certain times of the year, some of the lake water actually recharges back into the groundwater system. So you can look through time and try to uncover some of the dynamics of groundwater inputs and outputs from the Great Lakes. Next slide. Grand River, which we reside on here in Southern Ontario. We created a very high resolution model, including the even Strahler Order 2 streams and higher, very fine mesh. And we looked at a number of things with this. Andre Erder at Aquanty published a couple of papers recently, Water Resource Research, looking at dynamically downscale climate projections using the WRF, Weather Research and Forecasting Model. What did it do to mid-century, end-century groundwater levels, recharge, stream flows, etc. We also looked at contaminant transport. Next slide. Excuse me. So what we did, this was a study supported by Health Canada, looking at E. coli transport, E. coli arising from wastewater treatment plants, which are the red dots along the river. We also simulated a sulfame, which is an artificial sweetener, which behaves more or less conservatively. You know, artificial sweetener in soft drinks and all these kinds of things. You kind of know the loading, how much per capita people drink soft drinks and all these kinds of things. So we simulated this. And here it's just showing a pulse of the sulfate released from all the water treatment stations over a 1-week period. You can see it traverse the concentrations where it discharges in the lower right into Lake Erie. So we can actually do the transport. Next slide. We did this under low flow conditions, high flow conditions. Under low flow, you get higher concentrations over. This is sort of observation point is sort of going along the river from upstream to downstream. But under low flow, you get higher concentration because there's less dilution. Under high flow, you get more dilution, lower concentrations. So that was quite interesting. And the observations are actually falling more or less in between the sort of estimated high and low loading, reasonable loading rates for a sulfate from the water treatment plants. Next slide. And we also do some uncertainty analysis. We put together this PCM methodology. Killian Miller published that in advances in water resources a couple of years ago, 3 years ago. It's a very efficient method to handle uncertainty. Uncertainty, let's say, in parameters such as hydraulic conductivity or maybe other parameters. It's more efficient generally than Monte Carlo, or even more so generally than Latin hypercube. We were used in this example, order 2 polynomial chaos expansions, which resulted in 289 individual simulations, realizations, which converged. And you can see the uncertainty band in gray around about the mean value of the calculated concentration. So it's pretty good, and you can do uncertainty at a fairly large scale. Next slide. Now, I'll move on to another topic, HydroGeoSphere real-time hydrologic forecasting. This is a fairly new, well, we started it 3 or 4 years ago, but operationally it's quite new. Steve Fry and Derek at Aquanty sort of leading the charge on this development, and others. So at the heart is a HydroGeoSphere model of a watershed or a basin, for example. We have weather forecasts coming in. They're feeds. We don't just use one weather forecast, we use an ensemble. Because then you can get from an ensemble of weather forecasts, which are uncertain, some idea of the uncertainty in our hydrologic forecast. So HydroGeoSphere is embedded in there. You populate it with parameters, you calibrate it, and so on. And you begin running it, and you're driving with weather forecast. We also bring in real-time data assimilation, or data for assimilation. It could be satellite information, it could be groundwater levels with continuous feeds, soil moisture sensors, stream flow sensors, etc. Now, weather forecasts, reliability after 3 or so days, kind of not so good. The uncertainty increases. You see a deviation of the forecast of the hydrology from the observations. So data assimilation, we do a restart. We have a patent pending on this. Restart the simulation and go forward in time once again with the new forecasts. And so this is done, the model's continuously running, the updates or restart is done every couple or 3 days, and results all go into the cloud. We have a portal which you can look at the results, visualize it, pick on points, whatever you want to do, and it gives you the hydrologic forecast. Next slide. Currently, we do 7 and 32-day ensemble operational forecasts, and we do this for Southern Ontario, giving you surface flows, like stream flows, groundwater levels, groundwater recharge and discharge, and soil moisture. But you can view other things within the portal, as you'll see momentarily. And we've broken down Southern Ontario into all the major watersheds. So the outer model can drive the inner models at even higher resolution. Next slide. Working with Geological Survey of Canada, Ontario Geological Survey, they produced a fantastic data set for the subsurface, which we incorporated. We also included land cover, land use, and so on and so forth in building this model, calibrated it extensively, covers about 80,000 square kilometers. This is all available, all this data at the Geological Survey website, including the input data for HydroGeoSphere, should students want to use it and play with it. Next slide. You can also, in the portal, get other things like imagery of snow depth, soil moisture, soil temperature, 24-hour precipitation records, weather radar, and so on. So a lot of things available within the model, or within the portal. And this is just some examples, cloud-based hydrologic forecasting platform. So this is the Quinte watershed near Kingston. And what we're showing here are forecasts of surface water flows. Looks like it's going to begin raining there sort of midway along in time. Soil saturations, groundwater levels, groundwater discharge, groundwater recharge, whatever you want to look at. You can click at points to look at what's going on at certain locations with your forecast, or you can look at aerial maps to get a bigger picture of what's going on. Next slide. And this just happens to be surface water depths, a map of it. You can see maybe a little bit higher flow along one of the channels where it's deeper blue. Next slide. And here's recharge that was calculated or forecast within the model. So you get areas of higher recharge, areas of lower recharge. Similarly, you can look at maps of groundwater discharging to the surface water system. Next slide. Okay, I'll finish up now. A couple more slides. Expanding the scale. I had mentioned we had developed a prototype Canada scale model. It was published a couple of 3 years ago. This is a new project, a very exciting one, which involves integrated groundwater, surface water, climate modeling for climate change adaptation. It's federally funded. Our partners include Natural Resources Canada. I think Hazen Russell may be listening in. He's from the Geological Survey of Canada. He's a co-lead with Steve Fry at Aquanty. We also have Forest Service, Surveyor General Branch, the Mapping and Earth Observation people, Earth and Agri-Food Canada, University of Toronto, Physics, Dick Peltier and his group, along working with Andre Erler at Aquanty, are doing the climate projections, and University of Waterloo, we have close connections with Waterloo. Next slide. And there's a web, if you want to find out more details, there's that web link. You can, canada1water.ca. It's just at the beginning stages of this model, so don't expect results yet. So the idea is to develop a fully integrated model, groundwater surface water model for all of Canada. And one of the main priorities look at what might happen with climate change on a large scale. And the idea is to have a portal created so that everyone from policymakers to water managers to individual citizens can look at the results. It's a big area, I don't know, 10 million square kilometers. This is 3D. We've broken the area up into half a dozen sort of regional water basins that have similar physiography. Next slide. And so, again, we have to go through all the same sort of steps as you've seen in building previous models. DEM, major lake bathymetry, the surface drainage network, soils, hydraulic properties, hydrogeosphere, permafrost, all these things. Of course, we have to make use of historic weather, climate, calibrate the model, doing climate projections, existing databases, but also running WRF to produce an ensemble, not just one. So we can look a little bit at uncertainty. And then we also incorporate remote sensing into this model construction. And they have to be harmonized across the domain at a range of spatial scales. Next slide. So there's actually going to be kind of three types of modeling going on. There's land surface modeling using LSM, community, CLM, sorry. One of the things is it maintains a water balance. And in the north, where we're in Canada, northern Canada, more susceptible to climate change, we're very concerned about the permafrost dynamics. So LSM or CLM can give us some idea of the melting or whatever is going to happen to the permafrost, because that can feed into HydroGeoSphere in a hydraulic sense. Of course, we're also doing the regional climate modeling. We start from Peltier and his group, and Andre Erler has worked on this, running a global, typically NCARS or system model, and then telescoping in, usually in several steps, using the weather research forecasting model. Again, it's an NCAR product where you gain more physics, more resolution, and we can use those climate projections to drive HydroGeoSphere and hopefully get an idea of what's going to happen in the future. Next slide. I think I'm almost finished. So this just kind of lists, I don't need to read all of this. So the intent is to provide decision support to guide agriculture, forest, industry, rural communities, water resource planning, and so on. It'll be open source models and data to support future research initiatives. Perhaps graduate students can get involved. Down the road, what we hope to do is certain in selected basins or areas, make this real-time forecasting for deployment. We're not there yet, but we hope to get there. Next, final slide, I believe. So just listed here some of our lessons learned from experience. I think we've come a long way since the days of Freeze and Harlan. I think we understand processes much better over the intervening decades. There's always some missing data parameterized in terms of parameterization. A lot of it is now publicly available. For example, in Canada, there's the Canada 3D project within the Geological Survey, developed 3D digital geology of Canada. I know this is happening in other countries, including in Europe and Denmark and so on. There are still some computational challenges, but with parallelization, robust numerical methods, we can go a long way. All of these simulations that I've shown you were actually done on fast PCs. We didn't really necessarily have to go to a supercomputer. So that's a big advancement. That means a lot more people can do these kinds of things. And then advancing interface tools. Let the whole wide community look at the results coming out of these models and not just sitting in reports that only the technical people can understand and read. So with that, I think the next slide is thank you. Thank you very much.